Hello everyone, this is Pattern Recognition course number EEL6825 and the topic for today's presentation is prediction of stock prices using Keras and Google TensorFlow's deep learning model. We are now living in the age of the algorithm, and with the huge amount of financial data being generated every moment and the advent of advanced storage technologies, researchers are now determined to discover new techniques that can analyze the data at the speed at which it is being generated and make full use of it. We aim to develop a program which can predict the trends in the prices of the stock. The actual price of a stock can depend on a variety of data points such as the news, the company history, the industry trends, the dividend distributions. We can make educated guesses by studying a few of these data points, but to formulate a machine learning model which can take all the data points into consideration is next to impossible. So to limit the scope of this project, we are going to study only three kinds of data points for any given stock whose price needs to be predicted by our model. These three data points are gonna be the opening price of a stock for the day, the daily high point of the stock for the day, and the daily closing price for the stock for the day.
So what is a time series prediction problem? Time series prediction problem is the use of a computational model to predict the future values based on previously observed values against a timeline. In the context of data mining, time series analysis is a forecasting problem. Is stock market prediction a time series prediction problem? Yes, it can be considered a toned down version if we only consider model to forecast trends of the numerical data points against time instead of all the other factors described earlier that can affect the price of a stock. For the scope of this project, we limit ourselves to the time series based stock prices and other data points defined against time. We used historical data of New York Stock Exchange available freely on Yahoo Finance for non-commercial use as the input data. We can use a Python library called Pandas Data Reader to read the data from the internet and store it locally in the form of CSV for the use of our model. Neural networks tend to give better results if the input is converged. This pre-processing improves performance because the input data gets on the same scale. So rather than feeding the input data directly to our model, we normalize it. We do it to all the input data points by calculating the percentage changes from the initial stock price. This can be done by dividing the new price by the initial price and then subtracting the value of 1 from it. Later, when our model makes a prediction, we denormalize it by adding 1 to it and then multiplying the result with the initial stock price. Since our input data forms a time series, we can use a single neural network and supply it with the entirety of our training data, but this will restrict the size of the input and limit our network. So we can use a feed-forward neural network for our program. In this class of neural network comprises of various hidden layers of computational units typically interconnected in a feed-forward manner. That is, the hidden layers do not form cycles in themselves. The main problem with the feed-forward neural networks is that they do not have persistent memory and only take a fixed size vector as input. So, if we want the feed-forward neural network to predict, let's say, the next frame of a video, it will not be able to do it, as predicting the next frame of a video requires a series of image vectors that happen before the frame rather than just one time frame before the current frame. Consider a common scenario in the stock market known as correction. Here, if the stock has increased more than 2 to 3% of its value within a short span of time, people tend to sell the stock and the value of the stock again plummets and reaches its original state. So, the correction in the price of the stock not only depends on its price in the previous time frame, but it depends upon the price of the stock in a few of the previous time frames which led to the cost inflation in the first place. Because feed-forward neural networks only take into consideration one hidden layer before it and not multiple ones, which led to the correction in the price of the stock, a feed-forward neural network doesn't really fully satisfy our requirements. We need a way to allow information in our system to persist, and that's why we use a recurrent neural network for our project. A recurrent neural network can allow information to persist by accepting a sequence of vectors as input. So, while in a feed-forward neural network, the hidden layer's weights are based only on the input data, in the recurrent neural network, the hidden layer is a combination of the input data at the current time step and the hidden layer at a previous time step. The hidden layer is constantly changing as it gets more and more inputs, and the only way to reach the hidden state is with the correct sequence of input. This is how memory is incorporated in, and we can model this process mathematically shown by this equation, where the hidden layer at a time step t is a function phi of the input at time t multiplied by its weight matrix as we found in the feed-forward neural network, added to the hidden layer at the previous time step multiplied by its own weight matrix known as the transition matrix. This feedback loop is recurring at every time step in the series, and each hidden state has traces of not only the previous hidden state but also of all of those that preceded it, hence the name recurrent. Sometimes we need data from a time step a lot earlier than the current time step to correctly predict the price of the stock at the current time step. A recurrent neural network can overfit the training data and in such cases often predict incorrect results. Consider a scenario where Google has the Google I/O conference every year in March. The stock price of Google can undergo noticeable changes during this time depending on the success or the failure of the conference. So data points during March become outliers as compared to other data points. In a regular recurrent neural network, memories become more subtle as they fade into the past, since the error signal from a later time step is not able to make it far back enough in time to influence the network at an earlier time step during backpropagation. This problem is described in much detail in the paper titled "Learning Long-Term Dependencies with Gradient Descent is Difficult" by Joshua Benji. A solution to this problem is using long short-term memory. Long short-term memory network is a modification to the recurrent networks. In a recurrent networks, neurons apply an activation function to a linear combination of their inputs, whereas in an LSTM we replace neurons with memory cells. Each cell has an input gate, an output gate, and an internal state that feeds into itself across time step, a constant weight of 1. This eliminates the vanishing gradient problem, since any gradient that flows into this self-recurring unit during backpropagation is preserved indefinitely, since error times 1 still have the same value. Each LSTM cell has an activation function similar to sigmoid. During the forward pass, the input gate learns when to let activation pass into the cell, and the output gate learns when to let activation pass out of it. During the backward pass from the layers, which are a few time steps forward, the output function learns when to let error flow into the cell, and the input function learns when to let it flow out of the cell to the rest of the network. Everything else is similar to a recurrent neural network. Just updating this equation results in our network to be able to remember long-term dependencies. The clip art represented here is a visualization of an LSTM network where memory cells are feeding information to each other across time with different weights. After training and running our model to predict the trends for S&P 500 index for 50 time steps chosen at random places, we observed that for a lot of price movements in the S&P 500 index, especially the big ones, there is a good correlation between our model's prediction and the actual data. For our prediction with the price of the Google stock as seen in the figure, we see considerable similarities with our model's prediction and the actual data as compared to our prediction for the S&P 500 index. This is because to train our data set for the S&P 500 index, we only use one set of data points, and to train our model to predict Google's stock price, we trained our model on 3 sets of data points. We can actually observe that the more number of data points taken into consideration to predict the stock, the more accurate our model gets. This gives us the question, can our model be relied upon for making financial investments? The answer is gonna be no, as this is just an analytical tool to help us make educated guesses about the direction of the stock that is slightly better than random. To break down to conclusions, we can say that recurrent networks can model sequential data. At each time step, the hidden state is affected by the input and the previous hidden states. A solution to the vanishing gradient problem for recurrent networks is to use long short-term memory cells to remember long-term dependencies. We can use LSTM networks to make predictions on time series data easily using Keras and Google's TensorFlow. Are there any other good approaches to solve the stock price prediction problem? Yes, a very popular approach to predict the trends in the stock market is the sentiment analysis of the news regarding the stock in question and the economy in general. It is a good approach but incomplete in it itself because a lot of other factors like the company history, current prices and industry trends come into picture. Other approaches include using previous trends and statistical models to predict the stocks. All of these models cannot be relied upon 100% as they offer a prediction that is only slightly better than chance. A lot of proprietary algorithms exist which are used by machine learning experts to automatically select stock portfolios and place orders. And this is the demo of the project which uses a neural network to predict stock trends on the New York Stock Exchange. Here we are importing different sorts of libraries that we're going to use in our project. NumPy is used for matrix calculations, Matplotlib for plotting graphs, Pandas for Panda data reader for reading data from Yahoo Finance, and etc. And here we are actually passing on data to Pandas data reader for it to scroll Yahoo Finance and download a CSV file and save it locally on our system. This is the data that's available for today on the New York Stock Exchange. Here we are storing the three data points, that is the opening price, the closing price and the high price and the high point of a stock, in three different arrays, and we'll normalize it later over here. Here we are building our model and adding it's a sequential model with LSTM layers on it, and we'll train our model now. It's gonna take some time for the model to train, so I'll pause the video until the training is complete. And the training of our model is almost about to get completed, and it is now complete. Okay, so this is the output of our graph. It's generating the output. And here are the predictions. We can see as it's quite similar to the actual graph, and because there are a lot of other data points that affect the trends of the stock, we can generally see the trends that are predicted more or less. It can show us the direction of the market, but this cannot be relied upon like 100% to make financial investments. Thank you.